Hello students, I hope you are doing fine. This is lecture number 23 and 24, and we are going to discuss about discrete time signals. So the outline of today's lecture is we will start with the discrete time signals, how they are represented, and some basic sequences. We have already studied the continuous time version of those, right? So we'll be going through this quickly because you already know the continuous time version, so this would be only the discrete time version, right? And then how to combine two sequences, like operation on signals that we did in continuous time. Then classification of discrete time systems, again we have done this in continuous time, so we will doing the same in discrete time. So what is discrete time signal? Usually it is called a sequence, right? So discrete time signals are represented as a sequence of numbers, right? Because they have discrete values, they are not continuous in time. So they are represented as the sequence of numbers, right? Suppose a sequence of numbers x in which nth number is represented by x of n, right here, right? So here the independent variable is n in discrete domain, the independent variable in time domain is t, and in time domain the continuous time signal is represented as x of t, right? And where t is written in small bracket in parentheses. In discrete version, in some books it is written in parentheses the independent variable, which is n, and in some books it is written in square bracket like this one, right? So we'll be using square bracket from now on for discrete time signals. So x of n is basically a discrete time signal or a sequence where n is the independent variable, and n can have only integer values, unlike the continuous time. In continuous time t can have any value, any infinitesimal value, right? But n here can have only integer value, right? It can be negative, it can be negative. You can see here it expands from minus infinity to infinity, but it would have only integer values, minus 100, minus 99, minus 10, 1, 2, 100, 1000, whatever, but it cannot be 100.5, 100.25, something like that. So this the signal is formally written in this form: x equal to x of n, right? And to plot any discrete time signal, this is how it would look like. It would have discrete samples at discrete intervals, right? X-axis represents the values of n, and all these values you can see are integer values, and y-axis is the value of the sample. And between the values, so for example between -2 and -1, the discrete signal is not defined, it doesn't have any value. We usually assume it is 0, right? Although it is not defined, so we call it, usually these values are not defined at discrete intervals where n is integer. So basic sequences, as we did in continuous time, was unit impulse, unit step function, unit ramp function, exponential function, sinusoidal function. So we are going to discuss their discrete version here, right? So unit impulse in discrete time, it is called unit sample sequence, right? It is only one sample, right, that appears at 0, and it is 0 elsewhere, right? So it is represented by delta of n, and it is equal to 0 when n is not equal to 0, and it is equal to 1 when n is equal to 0. So unit sample sequence is often referred to as discrete time impulse only as an impulse, right? But most of the time we call it unit sample sequence. Now one of the important aspects of unit sample or discrete time impulse is that we can represent all discrete time signals as a combination of unit samples or unit impulses, right? For example, this signal p of n is actually combination of 4 impulses appearing at different time intervals, right? One at -3, 1, 2, and 7, right? So we can write down p of n as a combination of impulses, right? So here a3 is the amplitude of this impulse, and this impulse is appears at n plus 3, right? 3 time units ahead of 0, right? Or 3 time units on the left of the 0 is written as n plus 3. Then second sample appears at 1, and its amplitude is a1. So a1 and impulse delayed by 1 unit because it is on the right side of the 0. Similarly, this one also delayed, and its amplitude is a2 multiplied by impulse shifted by 2 units or delayed. This impulse is delayed by 7 units and its amplitude is a7. So this is how you can represent all the discrete time signal as a combination of impulses or unit samples. Or in general, x of n can be represented as k equal to minus infinity to infinity x of k multiplied by impulse shifted by k units. Right? Any signal can be represented in this form. Then we have unit step function. You know already that value of unit step is 0 when time is less than 0, and it is equal to 1 when time is equal to or greater than 0. Here the same definition applies. So it is equal to 1 when n is greater than or equal to 0, and it is 0 elsewhere. Then alternative representative unit step, as I told you, it can be represented as a combination of impulses. Right? So u of n can be delta n, this one, then delta n minus 1, n minus 2, n minus 3 up to infinity. Right? So we can represent unit impulse as a series of impulses. Right? We call it impulse train. Or in general, k equal to 0 to n delta n minus k. So unit impulse sequence can be expressed as the first backward difference of the unit step sequence, as given in this equation. Right? If you remember what is the backward difference is the current sample minus the last sample. Right? That is called the backward difference. So unit impulse can be represented as backward difference of two step functions, two step samples. Then we had exponential sequence. Exponential sequence is represented as x of n equal to a and alpha power n, where a and alpha are real numbers, and if they are real numbers then the sequence is real, and if they are complex then sequence would be complex exponential. So this in this particular example we are going to assume that a and n are real numbers. So we will have the real exponential signal. So now in exponential signal, it depends upon the value of alpha whether it is decaying or increasing exponential. Right? So when alpha is between 0 and 1, any value between 0 and 1, and a is greater than 0, then the sequence is actually decaying exponential. Right? As you can see in this figure, alpha is 0.5 and a is equal to 1, and n is independent variable. Of course, it increases from minus infinity to infinity. So here n has increased from 0 to infinity, or 0 to 10, and you can see as n is increasing, the amplitude of the x of n, which is exponential signals, is decreasing. Similarly, when alpha is greater than 1, it is increasing exponential. Right? So when alpha is greater than 1, when alpha here is assumed as equal to 2 and a is equal to 1, you can see that the sequence samples are increasing in amplitude with respect to n. And when alpha is negative, alpha is less than 0, we will have alternate polarity samples. The first sample, when n is 0, we would have equal to a. When n is even, we would have positive sample, amplitude sample. When n is odd, we would have negative amplitude. Right? So you can see here, when n is 1, we have negative sample. When n is 2, positive, 3 negative, 4 positive, 5 negative, and so on. Then the other type of signal that we discuss in continuous time was the sinusoidal signal, right? So continuous time sinusoidal signal, uh, here we have t in continuous time sinusoidal signal. Now we have replaced it by n in discrete domain, right? So x of n equal to a cos omega naught n plus phi, where phi is the phase angle, a is the amplitude of the sinusoidal signal, and omega naught is the frequency. And this is how it looks like when plotted against n. Now we'll discuss about the basic operations performed on independent and the dependent variables in discrete domain, right? So first we'll discuss about the operations performed on dependent variables, right? So dependent variables are actually the amplitude scaling. Amplitude of the signal is a dependent variable, right? So amplitude scaling means multiplication by a constant. So let's assume x of n represented here in this graph is a discrete time signal, and when we multiply this x of n with a constant c, then we get another signal which is amplitude scaled, and let's call it y of n, right, which is represented here in this figure. So c is called the scaling factor, right? So if c is equal to 2, for example, as it is shown in this figure, then the sample's amplitude would be increased by 2. You can see here in x of n, the first sample that appears at n equal to 1 has amplitude 0.5. Now it has multiplied with 2. Now it is equal to 1. Similarly, this amplitude of this sample is 1. Now it is 2, and so on. So amplitude scaling would increase the amplitude of the each sample, right? So it is sample by sample multiplication. The amplitude factor or the scaling factor would be multiplied with each sample. Then we have addition of two sequences, right? So for example, we have two sequences, x1 of n and x2 of n, and we want to add these two sequences, and let's say the result of these two sequences is y of n, and then it would be sample by sample addition, right? For example, as you can see in this figure, x1 of n is 1 2 3 4, right, and x2 of n is 0, and its value is 2, again 0 and 3. If we want to add these two sequences, then we will add the samples that appear at the same time interval. For example, sample at n equal to 1 and n equal to 1, here both would be added, right? So this sample would be added with this sample of x2 of n. So this is 0, this one is 0.5, the result would be 0.5, and this sample would be added with the sample at the same time interval, right? So n equal to 2, we have a sample having amplitude 1, and here n equal to 2, we have a sample having amplitude 2. So this 1 would be added with 2, the result would be 3. Similarly, this sample would be added with this sample, which is 0. So we have a sample with amplitude 1.5, and this sample would be added with this sample, right? So a sample having amplitude 0.5, and this has amplitude 3, so result is 3.5. So this is how the addition is done. You have to add the samples which appear at the same time, right? If there is a sample in this sequence, for example, which appears at 0.5, not 0.5, sorry, that appears at 0, for example, right, and have any sample here at 0, then you will assume that the sample value is 0 in this sequence, right, and you will add both this one plus 0, and you will write here, right. Similarly, the multiplication is performed by sample, right? The samples that appear at the same time interval are multiplied together. For example, considering the same samples x1 and x2, same sequences x1 and x2 here, and multiplication of these samples would be, this sample would multiply this one, result would be 0, of course, and this sample would be multiplied with this one, result would be 2, because amplitude of this is 1 multiplied by 2 would be 2. Again this sample's amplitude is 0, so this multiplied with this would be 0, and similarly 0.5 multiplied with 1.5. Now we'll discuss about the operation performed on independent variables. One of these operations is called time scaling, in which we multiply the independent variable with some number, and depending upon the number, the signal is expanded or it is compressed. So for example, when the number is between 0 and 1, as you can see in this figure, it is 0.5, the signal is basically compressed, right? So the samples that were at 0, 2, 4, now they are 0, 1, 2, 3. So it is compressed. And similarly, if the number is greater than 1, the signal is extended in time. You can see the sample that was appeared at 2 in actual signal, now it is at n equal to 4. So it is expanded, it is delayed. So signal actually expands on both sides of the 0. It's not just shifted, it is expanded symmetrically around 0. And other type of scaling is multiplication with a negative number, which is called time reversal, right? When time reversal is, for example, when n is multiplied with -1, signal is simply folded around 0. Now these are some example problems in which different kind of signal operations on independent and dependent variables are performed, and a new sequence is generated. And what you have to do, that x of n is given here, and you have to generate and plot the samples of the following sequences after performing the operation specified here, right? Now let me tell you what this arrow actually indicates. This arrow indicates this sample -5 sample is n equal to 0, right? So this is n equal to 0, so this is n equal to 1, n equal to 2, this is n minus 1, n minus 2, n minus 3, n minus 4, right? So the arrow here indicates that this is the sample value at n equal to 0. So I'm going to solve only the first one, and I would leave other two as a homework for you, right? So let's start the solution of the example problem A. So first I have plotted the graph of x of n, so that you can understand how the samples are presented. So this is the representation of x of n, and this is how it is graphically represented, right? So the sample at minus n equal to 0 is -5, so this n equal to 0 is -5. N equal to 1, we have sample value 8, and then n equal to 2, we have sample value 10. All other sample values are 0. And then at n equal to -1, we have 6. N equal to 4, we have n equal to -2, we have 4. At n equal to -3, we have -2, and n equal to -4, we have 1. And other sample values for values of n greater than -4 are 0, and similarly the sample values for the value of n greater than 2 are 0. So this is how the x of n is graphically represented. Now we'll have to find out first this one, x of n plus 2, and then multiply it with 3, right? So first we'll perform the operation on the independent variable, then on the dependent variable. Similarly, this one operation on the independent variable, it means the x of n is delayed by 4 units. Here x of n is advanced by 2 units and then multiplied with 2. Here x of n is simply multiplied with -2, right? Amplitude scaling. So we'll find out this one first, this one, and that one, and then we'll add these three together, right? So first we'll find out the 3x of n plus 2, right? So this is x of n. We'll shift it towards left by 2 units, right? It means the sample that appears at n equal to 0 in the shifted version, it would be at n equal to -2, right? Here you can see this sequence is shifted 2 units. So this sequence is shifted 2 units towards left side, right? So this sample is shifted at 2. Similarly, the sample that was at n equal to 1, now it would be at n equal to -1, and the sample like this one would be shifted to n equal to 0 here. So this is how the shifting is performed, and after shifting we have to multiply it with by 3, right? Time amplitude scaling. So after multiplication with 3, this sample would be multiplied with 3. Each sample would be multiplied with 3, right? And the result would be this one. So when x of n is shifted towards left, we get x of n plus 2, right? Now instead of at -5, we have 10 at n equal to 0, right? All other samples are at -1, n minus 1, n minus 2, n minus 3, and so on. And the sample values after n equal to 0 are 0. And then multiply this sequence. We have to multiply this sequence by 3, right? So each sample would be multiplied with 3. So 1 will be multiplied with 3, minus 2 would be multiplied with 3, and so on. So now this is the result of 3x n plus 2. Similarly, we will find out x of n minus 4 and then minus 2x of n, and then we can add all these together. Now let us find out n minus 4. X of n minus 4 is simply delayed version of x of n, right? So we have to perform delay of 4 units on x of n. So it means the sample that was at n equal to 0 now should be at n equal to 4, right? So you can see that minus 5 sample here is at n equal to 4, this one, right? It was at n equal to 0 here, now it is shifted to n equal to 4. Similarly, all the samples would be shifted 4 towards right. So now we have sample 1 at n equal to 0, right? So we have now x of n minus 4, which is equal to 1, minus 2, 4, 6, minus 5, 8, and 10. Now we'll find out minus 2x of n. So minus 2x of n is simply x of n multiplied with minus 2, right? So this is x of n, multiply x of n with minus 2. Each sample would be multiplied with minus 2, and the result would be 1 multiplied with minus 2 multiplied with minus 2, and so on, and you get the sequence here, right? So no shifting, only multiplication with the amplitude. Only dependent variable will change, independent variable remains same here. Now we have 3 cxn plus 2, x of n minus 4, and minus 2xn. We have to add these together, but for addition we have to add those samples with each other which have same index value. Same index value means they appear at the same time interval. For example, 30 here appears at n equal to 0. In x of n minus 4, 1 appears at n equal to 0, and in minus 2x of n, 10 appears at n equal to 0. So these would be added together. And similarly, 24 would be added with minus 12, and in this sequence there is no such value exists for n equal to minus 1, so we'll assume it is 0. Similarly, minus 15 would be added with minus 8, and result would be minus 23. 18 would be added with 4, we'll get 22 as a result of this, and 12 would be added with minus 10, you'll get minus 2, you'll get 10 as a result, and minus 6 would be added with 0 because no other value here, and 3 would be added with 0, you get 3. Similarly, for the values left on the on the left side, on the right side of n equal to 0, we have minus 16 added with minus 2 with 0, we have minus 18, minus 20 added with 4 with 0, we have minus 16, and then 6, minus 5, 8, and 10 same. So this is the result of all these operations performed here on x of n. So x1 of n is equal to 3 minus 10 minus 6, 10, 22, minus 23, 12, 41 is the sample that appears at n equal to 0, and minus 18, minus 16, 6, minus 5, 8, and 10. So same is solved here graphically, right? So we have 3xn plus 2, 3xn minus 4, and minus 2xn. So these three, added together, and the result is this one. Similarly, these three added. So graphically it is somehow easy, but it is more time consuming, right? So either you can do it mathematically like we did in the last slide, or you can solve it graphically. In either case, obviously the answer would be same. It depends whichever is convenient for you. So a system, we know that it performs some operation on the signal that is applied at the input, and it produces output, right? So in discrete time, let's say a discrete time signal x of n is applied, and it produces some output sequence y of n, right? So it is represented as y of n equal to t, where t is the function performed by the system on x of n, right? So it is graphically it is represented in this form, and mathematically we can represent system in this form. Now there are many types of discrete time systems. Actually, we have discussed all these systems in detail in continuous time, so we are going to going through this quickly, just show you the discrete version of those systems. So memoryless system, is a system that doesn't have a capacity to store energy, right? So output in memoryless systems depend on the current input, right? So if x of n is the discrete input applied to the memoryless system, then output produced by the memoryless system is y of n, and it would only depend upon the value of x of n. For example, y of n equal to x of n square, right? This system is a memoryless system. It only depends upon value of x of n, present value of x of n. Similarly, y of n equal to sine of x of n. This is also an example of memoryless system, and similarly this one as well. So memoryless systems are also called static systems. Memory systems are those systems which have the capacity to store information or to store energy, right? These are called the system with memory, or they are also called dynamic system, right? So they have one or more energy storing components. Their system equations actually contains differential equations in continuous time or difference equation in discrete time, right? You can see that here in output of dynamic system or system with memory depends upon the current value of input x of n, also previous value, right, that appeared 6 sample before. So if you see equation like this, it represents the discrete time system with memory. So you can actually identify the memory system by their equations. So the discrete time linear system has the same definition as the continuous time linear system, that it should follow the principle of superposition. So how we check the superposition of the system? We check superposition property by applying the linear combination of input first and then linear combination of output. In either case, the right side of the equation should be same, right? So if it is same, then it is linear, otherwise not. So the nonlinear systems are those systems in which input and output are non-linearly proportional or related to each other, like in this equation, y of n is equal to square of x of n. So if x of n is increased 2 times, y of n increases 4 times, right? So it is not linear proportion, it is non-linear proportion. So in simple way, 1 square plus 1 square is not equal to 1 plus 1 square, right? So here if input equal to 1 and two inputs equal to 1 are applied separately, and when both the inputs are combined together in light, result would be different. Then we have shift invariant systems, and the continuous time equivalent of this is time invariant system, right? So a system is called a shift invariant system if its input output characteristics do not change with time, right? The characteristics do not change with time. So how we can actually test this? We can test the shift invariance of any discrete time system by delaying the input and then computing the output, and then delaying the output and then comparing both. In both cases, if the system is shift invariant, the characteristics should not change. Then we have time variant system, that the characteristics of these system actually change with time. Then we have causal and non-causal systems. Causal systems are those systems in which we have the output that depends upon the present value of input and the past value. It doesn't have dependency on the future samples, the future knowledge, right? So the equation of causal systems would only contain x of n and delayed version of x of n, right? No time advanced version. If there is a time advanced version in the equation, then this system is non-causal, otherwise it is causal. So that is end of this lecture, and if you have any difficulty in understanding, you can email me. The email address is given on the first slide of the lecture. Thank you very much for listening.